I want you to picture a specific kind of genius. Imagine someone who has, well, arguably read everything. They've got the entire Library of Congress memorized, every Wikipedia article, every scientific paper.
Every recipe ever posted online.
Exactly. They can recite the legal code of France, they can explain quantum entanglement, and they
Mm.
can write poetry in the style of, I don't know, 17th century haiku masters.
Sounds like the ultimate dinner party guest. Or maybe the ultimate employee.
You'd think so, but here's the catch. You take this absolute genius, you walk them into a kitchen they've never seen before, just a normal kitchen, counter, an appliance, and you hand them a slice of bread. You say, "Make me a piece of toast."
And they just freeze.
Complete system failure. They panic. They know the dictionary definition of a toaster. They know the molecular structure of the bread, but they don't actually get that pushing the little black lever down causes the heating element to turn on.
They don't understand the physics of it.
Not at all. And that is, I think, the perfect summary of the paradox we're living through right now with artificial intelligence. We have these large language models, these LLMs, that are just the most knowledgeable systems ever built, but they struggle with the basic cause and effect of opening a drawer.
Which is exactly what we're getting into today.
It is. We're the learner profile here, so we are going to tear apart this really fascinating research paper. It's called Language Agents Meet Causality by Countouras and a few colleagues. It's a bit of a mouthful, but I honestly think this paper is like a missing link in AI evolution.
It really feels that way. The whole mission for this deep dive is to figure out how these researchers are trying to fix this toaster problem. They're trying to give LLMs what they call a causal world model.
A causal world model. That sounds very sci-fi.
It sounds fancy, but it's actually pretty grounded. It's really about building a simulator inside the AI's, well, its brain, so it can predict the future before it acts. Instead of just guessing based on words, it's simulating based on rules.
So instead of memorizing the manual, it's running a flight simulator in its head.
Exactly. And to get there, we're going to have to break down a few concepts, like causal representation learning and a framework they mentioned called BISCUIT.
I saw that in the notes. I'm really hoping BISCUIT is an acronym and not a snack because I skipped lunch to record this.
It is an acronym, unfortunately, for your appetite. But don't worry, we're going to skip the heavy math and really just focus on the logic. Because the logic here it's just fascinating, kind of challenges how we think about intelligence itself.
Okay, let's start with the problem, though, because I think a lot of people listening might be a little, meaning they've read about toasters a million times.
Exactly. They've seen millions of sentences where the words push lever and bread toasts appear close together. That's a correlation. But as we all know, correlation is not causation.
It's the classic rooster taking credit for the sunrise problem, right?
Perfectly put. The rooster crows, the sun comes up. If you train an LLM on that data, it predicts that crowing causes the sunrise. So if you ask that AI, hey, how do I stop the sun from rising? It might come up with a plan.
Kill the rooster.
Kill the rooster, which is a perfectly logical plan based on the words, but a completely failed plan in reality.
Right.
And in the paper, they call this hallucination in planning. When an AI tries to act in the world, or even a simulated one based only on these text patterns, it creates plans that sound linguistically perfect, but just fail physically.
They had that example about a locked box that I thought was really telling.
Yeah. An LLM might say, I will pick up the apple from the box. Grammatically, it's a beautiful sentence. It makes sense. But if the box is locked, the plan is garbage. The model doesn't have a physics engine to know that the state lock physically prevents the action pickup.
So it's like someone who's memorized the flight manual for a 747 but has never actually sat in the cockpit. They know what all the buttons are called, but they don't have that feel for how the plane reacts to turbulence.
And that lack of feel, that lack of a world model, is what makes current agents so brittle, especially if the environment is dynamic. I mean, if you're driving a car and a pedestrian steps out, you can't rely on a script from a book. You need to simulate the future right now. If I don't brake, I hit them.
So the goal is to install that simulator, a physics engine, which brings us to their solution, the causal world model. But this isn't just like plugging the Unity game engine into the bot, is it?
No, and that's a really key point. You can't just plug a video game into an LLM because the LLM doesn't see like we do. It sees tokens, it sees text. So they had to use a technique called causal representation learning, or CRL.
Okay, let's bring CRL down. How does an AI learn to see causality. Because, I mean, when I look at a video feed, it's just a bunch of colored dots moving around.
Think about how you watch a video. Let's say it's footage of a busy intersection. You've got millions of pixels changing color every millisecond. The sun's shifting, leaves are fluttering, a car is moving, a cloud passes over.
If I tried to track every single pixel, my brain would melt.
Exactly. Your brain filters it. You don't see pixel 4000 change from hex code hashtag FF0000 to hashtag F000001. You see the traffic light turned red. You see the car
You
accelerated.
see variables, objects.
You see high-level variables, light, color, car position, pedestrian speed. These are the causal variables. They're the hidden gears that actually determine what happens next. Everything else, the fluttering leaves, the clouds, the shadows, it's just noise.
So causal representation learning is basically teaching the AI to ignore the noise and identify the gears.
Precisely. And this is where that acronym comes in. BISCUIT.
Okay, lay it on us. What does BISCUIT actually do?
We don't need the full name, but the framework is brilliant in its simplicity. It identifies these variables by looking for changes that happen because of actions. It's essentially the toddler method of learning physics.
The toddler method.
A toddler learns physics by poking things, right? If I push this cup, it moves. Okay, cup position is a variable I can control. If I yell at the cup, it doesn't move. Okay, yelling is not a causal variable for the cup's position.
So the model watches the video and learns when this specific action happens, this specific part of the image changes.
And it builds a map. It maps that messy, high-dimensional visual world, the millions of pixels, into a clean, low-dimensional set of variables. It turns the video into a spreadsheet.
I love that analogy. It turns a video into a spreadsheet of variables. Light, red, car, moving, toaster, off.
Yes. And once you have that spreadsheet, that causal state, you can build a simulator. The LLM can now say, okay, simulator, what happens to the variables in the spreadsheet if I toggle the toaster switch? And the model just predicts the new state. Toaster, on.
It creates a little mental sandbox. It can play out the scenario in its head before it even moves a muscle.
That is the causal world model. It's the bridge between raw pixels and the reasoning part of the brain.
But here's the part that really surprised me, and I want to push on this a bit. Usually when we talk about robots and simulators, we're talking about hard math, coordinates, vectors. You know, move arm to X, 255, Y 120, precision.
Right, that's the standard robotics approach.
But this paper, they just decided to ditch the numbers. They went with words. They used natural language.
This is one of the most innovative parts of the research. They integrated natural language directly into the causal model. So instead of feeding the model mathematical coordinates for an action, they just used text descriptions.
So the system isn't calculating vector force. It's processing a sentence like, the cyan traffic light is showing a green signal.
Or, you toggled the toaster.
Now, playing devil's advocate here, isn't that worse? Language is fuzzy. Numbers are precise. Move 10 centimeters is exact. Move a bit to the left. That could mean anything. Why on earth would they choose the fuzzy option for a robot?
I had the same thought when I first read it. But think about who the user of this model is. It's an LLM, a large language model. It's a native speaker of English, not a native speaker of Cartesian coordinates.
So by using text, they're meeting the LLM on its own perf.
Exactly. By making the action space text-based, they remove any translation error. The LLM thinks in words, it plans in words, and now it perceives the world in words. It makes the agent a generalist.
I guess that makes sense, because toggle the toaster applies to every toaster in existence, but move to coordinate 5522 only applies to that specific toaster in that specific room.
Spot on. If you rely on coordinates, you have to retrain your robot for every new kitchen layout. If you rely on toggle toaster, the robot can walk into any kitchen in the world and understand the task.
But did it actually work? I mean, did the fuzzy words perform as well as the precise numbers?
This is where they used a term that I love, Pareto optimal.
Which is just a fancy way of saying.
In this context, it effectively means as good as the best alternative without losing efficiency. They found that the text-based representations perform just as well as the coordinate-based ones. But here's the kicker. In some cases, specifically when they had less training data, the text was actually better.
Words beat numbers.
In the low data regime, yeah. Because language carries baggage with it, useful baggage. It carries semantic meaning.
Right. The word toggle implies a switch flipping. It implies two states, on and off. The number 1 doesn't imply anything on its own.
Exactly. The text gives the model a hint about the physics before it even starts learning. It's a cheat code. It helps the model find those causal variables much faster because the language frames the problem for it.
That is profound. It suggests that language isn't just a way to describe the world, it's a way to compress the physics of the world.
Which, if you think about human evolution, makes perfect sense. We invented language to coordinate action. Throw the spear. Watch out for the lion. Our language is optimized for causal survival.
So they built this text-speaking variable hunting simulator. Now we have to talk about the showdown. They put this thing to the test against a standard, high-powered AI.
The experiments section, they used two environments. One was Grid World, and one was Ithor Kitchen.
Grid World sounds like something from an 80s arcade.
It's visually simple, but conceptually pretty tricky. It's a dynamic 2D simulation. You've got cars moving, traffic lights changing, obstacles like boulders, and the key word there is dynamic.
Meaning the world doesn't wait for you to act.
Right. In a game of chess, nothing moves until you move. In Grid World, if the light turns green, the cars go. If you're standing in the middle of the road, well, you get run over.
High-stakes Frogger. Got it. And the kitchen.
Ithor is a static 3D environment. It's a realistic, messy kitchen. Things only change if the agent interacts with them. The microwave doesn't open itself.
So we have a chaotic street and a quiet room. What was the task?
Two tasks. First one was causal inference, basically prediction. Here is the state of the world. Here is what just happened. What does the world look like 1 second from now?
And the second one?
Planning. Much harder. Here is where you are. Here's where you want to be. Figure out the sequence of steps to get there without failing.
And the opponent was Llama 3, and for you listening, Llama 3 is not a toy. This is a state-of-the-art open-source model. It's our smartest person in the room from the intro.
Correct. They use Llama 3 with a standard prompting strategy called reasoning via planning, which is basically just asking the LLM to think through the steps using its training data.
Okay, drumroll, please. Causal world model versus standard Llama 3. What happened?
It was a massacre.
Give me the details.
Let's look at the inference task in Grid World. Prediction. They asked the models to predict just one step into the future. The causal world model was over 95% accurate. The baseline Llama model, around 39%.
39? That's barely better than just guessing.
It gets so much worse. They then asked the models to predict 8 steps into the future, to simulate the next few seconds of reality.
Okay, so keeping the movie playing in your head.
The causal world model held strong. It dropped a bit, but it stayed around 75.8% accuracy. It can still see the future.
And Llama?
It flatlined. The accuracy dropped to 0.005.
Zero.
Effectively zero. Total hallucination.
Wait, so this super intelligent AI, the one we trust to write essays and code, couldn't predict what happens 8 frames later in a simple video game?
It couldn't. And this gets us right back to that noise versus variables concept. The standard LLM was looking at the whole image, all the pixels, the noise, and trying to guess the next pattern. It just got overwhelmed. It lost the plot.
Whereas the causal model was just tracking red car, row 4.
Exactly. It ignored the noise and tracked the truth. It proves that without a causal model, LLMs are effectively blind in dynamic environments. They can't maintain a coherent timeline of reality.
That certainly explains why we don't have self-driving cars powered solely by ChatGPT yet.
Precise.
Now, in the spirit of fairness, there was one area where the causal model struggled a bit, wasn't there? I saw something about put object versus toggle object.
Yes, it's not perfect. The model was incredibly good at toggle turning things on and off, 95% accuracy. But for put object, like putting a mug on a table, it struggled more.
Why is putting a mug down harder than turning on a switch?
Think about the math involved. Toggling is binary. It's a 1 or a 0, on or off. Putting an object down involves continuous 3D space, exactly where on the table, x, y, z coordinates. Predicting a continuous number is infinitely harder than predicting a binary state.
So it nailed the logic but fumbled the precision.
Which is what you'd expect. But here's the thing. For high-level planning, logic matters more than millimeters. If you're planning a dinner, knowing the chicken is in the oven is way more important than knowing the chicken is at coordinate 45.22.
That's a good point. It's high-level strategy versus low-level motor skills.
Okay, we have to talk about my absolute favorite part of this paper, the part that actually made me laugh out loud. Sub-N performance.
This was the surprise twist of the entire study.
So define sub-N for us.
In these experiments, the researchers set up problems where they knew the solution took a certain number of steps. Let's say 4 steps. That number is N. That's the ground truth.
So the humans who designed the test said the perfect score is 4 steps.
Right. But in the planning experiments, the causal world model sometimes solved the problem in fewer than 4 steps.
It beat the perfect score. How? Did it cheat?
It outsmarted the humans, or really, it outsmarted the assumption of how the task should be done. It found causal shortcuts.
Give me a specific example, because this is wild. Okay, in the kitchen environment, the ground truth trajectory provided by the researchers might have involved walking to the toaster, toggling it on, then toggling it off to check something, then moving away. The model analyzed the causal variables and realized, wait a second, if I toggle it on and then off, the state of the toaster is exactly the same as when I started. It's off, so I can just delete those 2 steps.
It realized the redundancy. It saw that doing nothing was more efficient than following the instructions.
And in grid world, it was even cooler. Remember, the cars move on their own. The model realized it could sometimes just wait. It could stand still and let a car move out of the way on its own, or let the target come to it.
The lazy genius strategy.
Exactly. But think about what that implies. To find that shortcut, you have to truly understand the physics of the world. You have to understand that waiting isn't just doing nothing. It's allowing the environment to execute a state change for you.
A model that just mimics training data would never do that. It would just copy the long, inefficient path it saw in the manual because that's how you're supposed to do it.
Correct. Mimicry repeats. Causality optimizes. This is the strongest evidence that the AI wasn't just guessing, it was thinking. It understood the rules of the game better than the people who designed the level.
That's actually kind of deep. It moved from knowledge to understanding.
That's the shift. That's the moment the light bulb really turns on.
So zooming out, we have a model that crushes the baseline, speaks English, finds shortcuts we didn't even see, but, and I have to play the skeptic one last time, these are still just grid worlds and fake kitchens. Why should you, the listener, care? We don't live in a grid.
The paper frames this as the current frontier. And yes, these are simple worlds, but they are a proof of concept. The vision is to scale this up.
Scale it to what?
To the real world. As these causal representation learning methods get better, we can plug them into this same framework. Imagine an AI assistant that doesn't just manage the text in your calendar, but understands the causality of your schedule.
If I book this meeting at 9 a.m. in downtown, he physically cannot be at the airport for his 10:30 flight because traffic exists.
Exactly. Right now, AI is often just a fancy autocomplete. If we add a causal world model, it becomes an agent. It moves from entertainment to utility. It moves from writing a recipe to eventually cooking the meal.
Or at least knowing not to put the metal fork in the microwave.
We could hope. But it's really about trust. You can't trust an agent that hallucinates its plans. You can trust an agent that simulates the outcome, sees the crash in its head, and says, actually, let's not do that.
It's the thinking before acting module that AI has been missing.
Precisely.
We're coming to the end of our deep dive, and I want to leave everyone with that sub-N thought again. It's been sticking with me since I read this.
It is the most provocative part, I think.
We saw the AI find shortcuts in a simple little grid. But the real world, our economy, our climate, our biology, those are just massive, unbelievably complex causal systems.
They are. And we as humans are limited in how many variables we can actually track. We see correlations, but we often miss the deep multi-step causal chains because our brains just can't hold that much data.
So if we can build causal world models that actually scale, if we can build an AI that truly understands the physics of the economy or the human body,
we might find that the solutions to some of our biggest problems are sub-N.
we might be doing things the hard way simply because we can't see the shortcut.
Exactly. We might be toggling the toaster on and off, thinking it's a necessary step, while the AI is looking at us and saying, you know, you can just skip that, right? You can cure this disease in 3 steps, not 50.
That is a hopeful and a slightly humbling thought to end on. Maybe the robots will teach us how to be efficient after all.
I certainly hope so.
Well, thank you for guiding us through the matrix of causal world models today.
Always a pleasure.
And to you, the listener, thanks for diving in with us. Next time you make toast, appreciate the complex causal physics required just to get that perfect crunch. This has been The Deep Dive.